Today we're going to take a look at section 1.4. 1.4 is all about linear equations. So we're going to look at a lot of different features. We briefly touched on some linear equation stuff last time. We looked at horizontal and vertical lines specifically, but we're going to delve farther into linear equations today. So first of all, we're going to take a look at a definition for slope. And in particular, these would be slopes of lines that really didn't fit into that, especially the vertical line component. Horizontal line works okay with this, but in particular, we're looking at things that we might call diagonal lines or something like that today. So the slope of the line through the points x1, y1, and x2, y2 is defined as, we call it m, and it's y2 minus y1 over x2 minus x1. It doesn't really matter which point you identify as x1, y1, and x2, y2, just so long as you stick the ones with the subscripts 1s together and the subscript 2s together. So we've got an example here. We have the point 2, -1, and 5, -3. And I usually just go in order of what they're given to me as. So x1, y1 here, and x2, y2 here. And so if we're finding the slope, we will take the second y value, which was -3, subtract the first y value, which is minus and -1 then. Okay, so don't forget that there's a subtraction sign within the equation for slope itself. And then I take the x2 value, which is 5, minus the first x value, which is x1, which is 2. Okay, so if we simplify, we recognize first and foremost that we've got minus and negative right here. So that's going to be addition. And so I actually have -3 and +1, which gives me, -2. And in my denominator, I have 5 minus 2, which is 3. If it could reduce, we would, but -2/3 does not have that capability, so we're done at the point when we get to -2/3. Okay, I have a couple more that I'd like to show you what happens. So again, we're going to identify x1, y1, x2, y2, and find our slope. So the second y value is 3, minus the first y value is 3. And hopefully if you see that right now, you're thinking, oh, what do I have on top? 0. Let's do the denominator just so that we can see that we don't have 0 over 0, because that would pose something else entirely. It would mean that our 2 points are the same, and they're definitely not. But I then have -10 minus 7. So sure enough, I have 0 on top, and I don't have 0 on bottom. In particular, it's -17. But when you divide 0 by anything that's not 0, you get 0. So this is a slope that's 0, and we encountered that last time when I talked about Hooy-Vux. And in particular, we found that happening when we got to the 0 slope. This is a horizontal line. I have a line that has the same y value at every point if there's a line connecting these two ordered pairs. And then I have one more. So again, x1, y1, x2, y2. You don't have to write that down. I'm just doing it for the purposes of us being able to see it together. So the second y value, is -3 minus the first one is 9 over the second y value, the second x value is 4 minus the first x value of 4. And here I end up getting a 0 on the denominator, right? So I have -12 on top over 0. Again, in particular, I just have something that's not 0 over 0. So anytime you have this happen, what happens is you get an undefined slope. And undefined puts us up there in that second part of the Hooy-Vux description from last time. The U, this is a vertical line that's actually being described by the connection of these 2 points. Now, we weren't asked to identify horizontal and vertical lines, but they are, in fact, those type of lines, just the slopes. We have several types of forms for a line, like equations for a line. We encountered standard form before. If you'll remember, it looked like this: ax plus by equals c. At least I think we did that in this class. Might have been my other class. Sorry if I'm saying things that aren't true. There are some conditions on a, b, and c here. They have to be integers. Okay, so a, b, and c are integers. So no fractions, no decimals for it to be in standard form. And the a value is bigger than 1. I didn't say, yeah, it's not bigger than 1, bigger than 0. It's positive. There we go. So I guess it is actually bigger than 1 because I'm looking at whole numbers, but yeah. So I need it to start with a positive value. That's considered standard form. Standard form's not all that helpful. We did encounter it at one point last class period where we talked about if it's in standard form, it's actually pretty easy to find an x-intercept and y-intercept. But I can't take something in standard form and easily plug it into the calculator to solve. I don't have easily identifiable the slope and the y-intercept from that form. The best thing that standard form does for us is what we'll have happen in chapter 5, which has to do with solving systems of equations. So when I have 2 sets of equations, it's one of the ways that I can solve equations from that perspective. But it's not all that useful, generally speaking, for solving equations of their own, like simplifying or finding certain features. The point-slope form and the slope-intercept form both are. They're a little bit different, and they kind of highlight different pieces of information. So in particular, if we have the slope m and we have the point x1, y1, then the point-slope form is y minus y1 equals m times x minus x1. This form is very convenient for finding an equation of a line because oftentimes we are given the slope and some point, but not always the y-intercept, just any kind of random point. It's also nice because you can actually see the slope. It's visually right there, right? There's no question as to what's the slope like it would be if I had ax plus by equals c. And I can actually see a point as well that is on my line. So there's some nice features to this one. Maybe a not nice feature is that it doesn't look very simplified. Right? Y is not alone. I have some parentheses that are still involved. So it doesn't sort of look like it's finished, in a finished form. The other one is the slope-intercept form. And the slope-intercept form is probably the one that we most frequently think of when we think of lines. Y equal mx plus b. And it also has some really nice features, right? You can actually see the y-intercept and you can see the slope at a glance. It's set up so that it's actually directly enterable, if you will, into your calculator. That's kind of friendly. It has a lovely simplified look to it. Right? It doesn't look like it's still sort of in progress. But it's not always necessarily the easiest way to start a problem if you're trying to find things that don't specifically give you the slope and the y-intercept. So sometimes we don't always start there. So we're going to do some some examples where we create equations. And when we are solving these equations, at the end of the problem, we are in fact going to want them, unless we're told otherwise, we're going to want them to be written in slope-intercept form, the last one, okay? So we're going to consider our question completed when we have it saying y equals and everything else on the other side is simplified, okay? Again, unless it says otherwise. So this is an example where I'm given the points, and we actually did this one before. I did this one as the first example over here. So we've already found the slope here. So I'm just going to copy and paste mine over there because I don't think we need to find it again. But if we hadn't found it, of course, that would be our first step. So the first thing to do is to find the slope. Okay? So we have our slope. If you want to put just a reference, just say same as problem number 1 or something like that, if you don't want to rewrite all the pieces. Because we're given, or found, I should say, it's because we found the slope and we're given at least one point. It's very nice and very friendly to use the point-slope form because I have a point and I have slope. And I get to pick which point I want to use. It doesn't matter which point I use. I just need to pick one. So I'm going to pick the first one, not for any particular reason, just because it's first. Right? If you pick the second one, you're going to get the same equation, I will. So no fear on that. And I'm going to use that point-slope form. So y minus y1 equals m times x minus x1, like so. And I found the slope earlier, but I found it. And this x1 and this y1 in here are going to compare or be used with the point that I chose, which was 2, negative 1. Or if you want to, you can choose 5, negative 3. So we're going to evaluate, substitute into that. So my y value is negative 1, so this is minus negative 1. My slope is negative 2/3. And then x minus the x value, which is 2. Now, this is not a very pretty one to work with, simply because it has the fraction. We can do it, but it's just not very friendly. So we're going to simplify a couple things. First, we notice that we have minus a negative on the left. So this is really y plus 1 on the left. And then on the right, we're going to distribute the negative 2/3 in through the parentheses. So we have negative 2/3 x, and then we have negative 2/3 times negative 2, which is positive 4/3. 2 times 2 is 4. Remember, this is like having 2/1 in here. So we've actually eliminated the parentheses. That's a good first step in simplifying, cleaning this up. The last thing is that this y, to be alone, I need to shift the negative 1, or shift the 1 by subtracting it to the other side. So I will subtract 1 from each side. So on the left, I now have the y that I was looking for. I have the negative 2/3 x. And I need to combine these two pieces right here. And it is subtraction, like not division, it's actually subtraction. So 4/3 minus 1. Well, minus 1 means I need a common denominator. 1 would be the same as 3/3. So 4/3 minus 3/3 would give me 1/3. And if, in fact, this equation is true, if it actually works for what we just found, we should be able to take each of our ordered pairs, one at a time, and plug them in for x and y and get statements that are equal on both sides. Right? That's what it means for those 2 points to lie on that line, is they have to satisfy that equation. So you could check it that way with the information that we actually started with. Any questions on that one? Okay. You'll notice that the next one is the next example that we had encountered. The one it was number 2. So on number 2 over here, I found that my slope was 0, right? So I'm going to again copy and paste this since we've already done it. We found the slope to be 0. So there's a couple of different things you could do when the slope is 0. One is that you could simply remember that acronym HOIVUX, recognizing that you're in the first half of it because you have a 0 slope. Therefore, it's a horizontal line, which means that it's y equals, and it's y equals the number that they had in common, which is 3. So if you happen to remember that acronym, if that sort of resonates with you, that's great. If not, you can use the point slope form like we did on the last equation. Okay, like this. And the m value is simply 0. And because the m value is 0, the right-hand side just eliminates itself immediately because you've got 0 times whatever comes next. And if I'll just use the first point again too, 7, 3. So this would be minus 7 over here. And then this would be y minus 3. So if I actually simplify that piece, let me shift that up just a little bit, I have y minus 3 equals 0, or y equals 3. You don't have to do it that way. If you happen to recognize, again, that you're in the HOI part here of HOIVUX, you simply know that the equation is y equals, and it's y equals 3 because 3 is my common y value. And then number 6 is, of course, the number 3 that we did before over here. So I found my slope over here, and it is undefined. Now this one's a little bit trickier in terms of I don't really have the ability to use the equation that's the slope intercept, or the point slope equation. And the reason I don't is because I don't have a slope. It does not have a numerical value. It is, in fact, undefined. So there's nothing I can actually plug in for m. It doesn't exist. It's not possible. So I really do have to, on this one, I don't have a choice, but I have to rely on the fact that this is a vertical line. When I have an undefined slope, I do, in fact, have a vertical line. Vertical lines have the equation x equals, and the x value here is 4. So it's x equals 4. Any questions? Now on all 3 of those, we had to find slope. We did it earlier, but we'd have to find slope because we were given 2 points. Sometimes they actually just give you the slope, like this one. They give you a point, they give you the slope. That's even friendlier because you don't have to make any choices, right? I don't have to pick a point. I only have 1 point they're given to us. So I'm going to use that same y minus y1 equals m times x minus x1. And so my x1, y1, and my slope all become substituted into that form. So y minus, the y value is 9. My slope given to me was negative 1/3. X minus my x value is 6. So on the left-hand side, it's just y minus 9. On the right-hand side, I need to distribute the negative 1/3. So again, maybe not quite so friendly because I have fractions involved, but it's friendlier than the last fractions when I did. And the reason is because the negative 1/3 times the negative 6 is actually a whole number. What is 1/3 times 6? Yeah, it's 2. And it's addition because I had 2 negatives there, right? A negative on the 1/3 and a negative on the 6. So this one's actually friendlier than the last fraction when I did because I do end up with a whole number when I multiplied it by that 6 at the end. So then when I add my 9, it can combine very nicely with that 2. And my equation is y equals negative 1/3 x plus 11. All right, so far so good? Okay, so the next thing we're going to take a look at is what happens when we compare types of lines. There are two special types of lines that we're going to take a look at, and those lines are parallel lines and perpendicular lines. So parallel lines have the image you would think of like a train track, right? The two lines never get any closer or never get any further away, otherwise the train would run off the track. Okay. Now, the difference is that, of course, those parallel lines are not always linear on a train track. Like they can turn and so forth, and ours don't have that ability. But our lines are parallel, in particular, if they have the same slope, right? Because if they have the same slope, then the degree to which they incline has to match, and so therefore, they have that sort of a same distance perspective that we have when we think about lines being parallel. But by definition, they actually have the same slope. So this is a really important feature that we have to keep in mind as we're solving and working with them, that we're looking for things with the same slope. Perpendicular lines, even if we can't justify exactly all of this description, part of it you certainly can. So lines are perpendicular in particular if they form a right angle when they cross, right? It's not a very good right angle, but pretend. So at the very least, you should be able to look at this and say, yes, I've got a negative slope and I've got a positive slope in order to make that happen, right? So that's what's creating the crossing to begin with, is that the slopes are not matching. And then the idea of them crossing at that 90-degree angle comes from the fact that the slopes are actually reciprocals of one another, in particular negative reciprocals, okay? So we've talked about reciprocals, I think, before. So if we have the number 2/3, then the reciprocal would be 3/2, right? It's just the flip of the fraction. And one of them has to be positive, one of them has to be negative in order for them to actually be slopes of perpendicular lines. If we have whole numbers, like let's say we actually had a whole number or an integer, we say we had the number -5. -5 is the same as 5/1. So when I flip it, it's 1/5. And I use the opposite sign. So it's positive. Well, you'll usually be given one of them and you're trying to find the other one. It's just whichever one it's not. Yeah, exactly. So, but in order for them to actually have this relationship, one has to be positive, the other one has to be negative. So let's take a look at an example of how that plays out. So we have an equation given to us, and unfortunately, because it is really an actual unfortunately, it's given in standard form. And the reason that that's unfortunate is because, as I mentioned before, I cannot easily identify what the slope is just by looking at the way that the equation is set up. Agreed? It's not evident, apparently, immediately, is what I meant to say. Not evident immediately. So we're going to have to find the slope. In order for them to be parallel, the slopes have to be the same. So I need to figure out what the slope is, and then I'll use that slope that I find along with the point that I'm given, and I can create my own line. Now, they do want us at the very end of this one to write the equation in standard form. So this is an example of one where the directions are not what I said earlier, right? I told you that that might happen. Unless you're told otherwise, we're going to write the answer in y equals form. Well, we're being told otherwise here. So when we're done with this problem, we are going to write it in standard form, okay? So taking a look at this equation, the first thing we're going to do is we're actually going to find y equals. We're going to find the slope by changing the order of things. So I need to have y alone, so I'll move my 3x. So I have negative 6y on the left. And I'm looking for mx plus b form, so I'm going to put the negative 3x at the beginning and then the positive 7 afterwards. Okay. And then I need to divide by negative 6. And while it's true you can write it like this, and that's correct, it's probably a little bit more helpful to remember that you can also divide it like this. And the part that we actually care about is this part. So while I have a 7 over negative 6 on the right-hand side, it's irrelevant to the part of my question that I'm working with. I don't care about that piece. So I would like to reduce negative 3 over negative 6 if possible, and it is possible. So what is that going to be if I reduce it? 1/2. So this is 1/2 x, or you could write 1x over 2 is fine. So my equation actually looks like this, but the only part that I really need is the 1/2. Okay, so my slope for the equation given is 1/2. And because I'm creating a parallel line, I want to use that slope. And I want to use the other point that I'm given. So at that point, and let me shift this up a little bit. At that point, I'm going to use y minus y1 equals m times x minus x1, just like before. My m value is 1/2. My x value is actually the negative 4, so I have x minus negative 4. If you can jump to just x plus 4 because you see it, that's fine. On the other side, I have y minus the y value, which is 2. Now, I do, in fact, need to distribute this through. I'll do that. But remember, my goal at the end of this problem is for it not to say y equals something, but for it to have the x's and y's on the left, and then anything without an x and a y, a constant on the right. That's my goal at the end of this problem. So as I simplify this, I'm going to be doing things a little bit differently than I did before. So I have y minus 2 equals, I have 1/2 x. Now this is, like we said, a positive, so I have x plus 4. So what is 1/2 times 4? It's 2. So then I have plus 2. So anything that has the x's in it needs to move to the left. So I'm going to subtract the 1/2 x like this. And if you can, you're welcome to do this in one step where you're also moving the 2. So, like that. Just shifting this. And you can add the 2 to both sides at the same time. If you need to see it in 2 steps for it to be more comfortable than do 2 steps, it doesn't matter to me. So I want the x to be listed first. That's negative 1/2 x. I want the y listed second, so plus y. And then on the right-hand side, what do I have? I have 4. Now we're really close. We've got it in the x, y number form. But that x coefficient at the beginning needs to be positive, and it needs to be a whole number, right? Or an integer, right? Which a positive integer is a whole number. So I need it to not have the negative 1/2. So how can I change everything so that I will not have a negative 1/2 associated with my x? Yep. And not just 2, but something else a little bit. Negative 2. So I'm going to multiply by negative 2. Of course, you cannot just multiply one piece of an equation by negative 2. You have to multiply everything by negative 2. So the first piece, which is now x, you can put a 1 in front of it if you wish. And then I have negative 2 times y, so I have negative 2y. So I don't have a positive y, but that's okay. And then I have negative 8. And that would be standard form.
It's only the a
What?
has to be positive.
Correct. It's only the a next to the x that has to be a positive. Correct. But all of them have to be non-fractions. So if I had more than just the 1/2 here, like maybe there was a 1/4 inside there too, I would have to take that into consideration when I figured out what I needed to multiply by, because I got to eliminate all the fractions. Okay, I think I have one more of these. Two more of these, in fact. Okay, so have another example, but this one says perpendicular, yeah? Okay, so if they're going to be perpendicular, their slopes are not the same. They're negative reciprocals, but I still have to find the slope in order to make that happen. Agreed? So the first part of these two problems looks the same. I need to get it to say y equals and figure out what my slope is. This one's a little bit easier to work with, just a little bit less going on. So I'm going to subtract my x. So I have negative 2y equals, and I'm going to put the x first, negative x plus 3. And then I would divide by negative 2. Again, a little bit more helpful just to write each individual term divided by negative 2. So this is y equals. Now I've got negative x divided by negative 2, so what will happen to the negatives? Yeah, they become positive or they cancel out. So this ends up being x over 2, or if it helps you to think about it in a moment here, this is 1x over 2. And then I have negative 3/2. Not that I need it, but it's there. So my slope is actually 1/2, right? So the slope here, m, is equal to 1/2. But the slope of the line that I'm finding is not going to be 1/2. What is the slope of the line that we really are finding going to be? Negative 2. So there's a notation that we're going to use, and I'll write it down up here. I'm trying to figure out where my space is the best. This is a symbol for meaning perpendicular. It kind of looks like two lines forming a right angle vertically and horizontally. So the slope of the perpendicular line would be negative 2. That's what we're going to be using here. So I have this slope, and I have this point. That's a little nicer because I don't have fraction. It's the first non-fraction one we've done today. So we have y minus, and the y1 value is 1, equals my slope, negative 2, x minus negative 3. I'm still using the same direction sets I had over here where it says find the standard form. Just so you know, just because I switched slides and it's not there, it's still the same direction set. We're still doing the same type of problems. So I want to clean this up, but my goal is to have x and y on the left. So I have y minus 1 equals, I have negative 2x minus 6. What would I do next? Add the 2x and add the 1. In the same step, in two separate steps, doesn't make any difference to me. This gives me 2x, so of course these add to 0, plus y equals, and these add to 0, and I have negative 5. So on this one, I'll highlight it since my types are all running into each other. At this point, I'm finished on this problem, because I do have all whole numbers, right, all integer values with the positive a at the beginning for a 2. Yeah, Tori?
It doesn't say that in the standard form, so could we have left it?
Okay, but this direction set is the direction set for these two slides.
Oh,
Like,
I didn't
it's
know
just-
they're two different.
What's that?
Never mind.
They're just split between two slides, and I didn't copy that over. So it's the same direction set. It won't be unclear in your homework because they put them in these like chunks of questions, and you'll know. So this would have been in the same chunk of questions, basically. Okay, I think there's another one. So number 10 actually gives us a line of a very special type. It says x equals 7. Here's my notes. Okay, so x equals 7 is what type of a line? It is vertical. This is a vertical line, right? It goes like this. That's not super straight, but pretend it's straight up and down, okay? It's a vertical line. So if I'm going to create a perpendicular line to this, what will it look like? It will look horizontal. So the line that I'm looking for will be much like this green line. Like I said, my white line's not super straight, but pretend. Okay, it has to be a horizontal line. So the line that I'm looking for will have to be horizontal. A horizontal line, right? Think again, Hooyvaks. A horizontal line has an equation of y equals. Well, it's y equals, but it has to go through this point. what does y equal?
2.
2. So there's no work that I have to do, like number crunching kind of work for this. But I do have to recognize the relationship that's happening. Now let's say you get to a question like this and you're having a very difficult time piecing together the acronym or remembering those pieces of it. Maybe you're in the middle of the quiz and you're just blanking. You can always draw a picture of this, correct? So if you were to actually draw this actual picture over here, let me cut this for a sec. And you had a axis, so this is now my axis. And you had the line x equals to 7, so you'd go 1, 2, 3, 4, 5, 6, 7, and you'd draw your line in there. And your line would look something like, let's use pink. Looks like this. And then you have the y value, or this ordered pair, 1, 2. You'd go over here and you'd count over 1 and up 2, and you'd have this point right here. So you need it to be going through that point, and it has to be perpendicular to this line, and you can actually draw that in, right? Looks like that. And then again, you can make the assumption, not the assumption, but make the observation then that every y value is the same. All the y values along that line are 2. So you can think of it from that perspective if it's more clear or easy to do so from that.
Is that the same form of
It is. So there's not a way to write it as ax, y, I mean, all those pieces together. This one has its own form, or y equals 2. And the same thing would happen if you were given like the y equals 2 and told to do the same directions, is that it would say x equals 7. So for horizontal and for vertical lines, they simply are x or y equals, and that's all you got. Yep, good question.